Okay, so today we will start chapter 3. This is a chapter on the topic of motion along a straight line. So this is one-dimensional motion. For example, motion along the plus x direction and the minus x direction, right? No motion in y, for example. So what are our goals for this chapter? Our goals are to understand the concepts of displacement, velocity, and acceleration. These are all words you may use in everyday life, but we want to define them mathematically and understand the concepts of them physically. We want to read and interpret position versus time, or x versus t, velocity versus time, or v versus t, and acceleration versus time, or a versus t graphs. These are really critical for our conceptual understanding of motion and really useful. These are things you may see in everyday life, working as an engineer or in many other fields. Another goal is to learn how to describe a very special case of motion along a straight line, which is constant acceleration motion. Not all motion has constant acceleration, but when you do have that special case, there's certain equations we can use that apply only to that special case, and it enables us to solve certain problems. And finally, our goal is to learn how to solve problems using these concepts. Again, this is our first real physics chapter, so we're going to learn a lot about the method of solving problems in physics. Okay, to get started, let's just remind ourselves of the concept of position. In one dimension, we're just going to draw a number line, right? We're going to define some location to be 0, and we're going to define one direction to be the plus x direction, another direction to be the minus x direction, and we'll just measure our position on this number line. So this red dot is at the position of x equals 3 meters. Okay, in two dimensions, we're going to draw a plus x and a plus y axis, and we're going to define our position specifying both of those numbers, right? So the position of this red dot is that x is equal to plus 2, y is equal to 4 meters. Okay, and so we could specify this position using those two numbers, 2 meters comma 4 meters, for example. Okay, so that's the concept of position. Now we want to introduce the idea of a position vector. Right? A position vector is a vector which originates at the origin and points to where you're located. Okay, so it still requires us to define a coordinate system. So again, we're going to define the same coordinate system in one dimension. We define an origin, we define a plus x direction, and my position vector is again just going to start at my origin and point to where my location is. The magnitude of this vector is going to be how far away I am from the origin. All right, so I'm 3 meters away from the origin, and the sign of it, if it's plus or minus, is going to tell me the direction. All right, so this is a vector, so I write it as r with an arrow above it to say this is my position vector. We're typically going to use the symbol r for position vector. The component of this vector is 3 meters, positive 3 meters, in the I hat direction, meaning we're along the plus x direction. Okay, the component of this vector is right in here, that is 3 meters. Okay, now in two dimensions, we're going to again specify our location using two pieces of information. So I want to draw a position vector for this red dot. Again, I'm going to start at the origin and draw my vector at a point at that point. And to specify its x and y components, again, I need to do 2 meters I hat to specify the x component and 4 meters j hat to specify the y component. Okay, so that's a two-dimensional position vector. And so I wanted to define these because we're going to use these concepts to define things like displacement. Before we do so, I just want to make a few notes on notation. Okay, and this is something that's necessary because so many books use different pieces of notation, and I just want to make sure everybody's clear at the start what notation we're using when we're using all these subscripts and things in this class. So often subscripts are going to be used to denote measurements made at separate times. So if I do t sub 0, that means the time is equal to 0 seconds, right? Whatever we're defining 0 time to be, t sub 0 is that time. Okay. T sub 1 is going to be just time measurement 1, our first measurement. T sub 2 is going to be time measurement 2, our second measurement. Time measurement 2 is always going to come after time measurement 1. Okay, so that's the first note on notation. The subscripts used to denote different moments in time. We will commonly use these times as subscripts in other measurements. Right, so for example, E sub 0 would mean the energy when the time equals 0. E sub 1 would mean the energy when at time 1. E sub 2 would mean the energy at time 2. And sometimes we may also specify a given energy or something else by plugging in a given time to a functional form. So I may know my energy as a function of time, right? I may have an equation for my energy at any given moment of time. So if I plug in to that functional form time 1, then I would find out what is my energy at that given time. Okay, so that's another way of specifying a given energy. And also sometimes your book and other books are going to use initial and final instead of time 1 and time 2. And so we just need to be ready for that and just know that that exists. So E sub I would mean the energy of an object at the initial time. E sub F would mean the energy of an object at the final time. Right? So final would always come after initial. Okay, so continuing our notes and notation, I'm going to introduce a new symbol, this delta symbol. Okay, so it's the Greek capital letter delta. And so this notation means a change in a quantity. So it's always going to mean final value minus my initial value. All right, so that's just conceptually, what does this delta symbol mean? So if I have, for example, delta t, right, that means the change in my time, and so it's or the amount of time that's elapsed. Right, so it's going to be t2 minus t1, my final time minus my initial time. If I did delta P, that's P2 minus P1, that's the change in my pressure. And delta P could be positive if the pressure was getting bigger at my later time, or it'd be negative if it's getting smaller. If P2 was smaller than P1, my delta P would be negative. Okay? And just again, using some of the notation from the previous slide, delta E is my change in my energy. It could be E2 minus E1, or I could be using the notation of final and initial, in which case it would be E final minus E initial, or I could be using the functional form of my energy, and that would be a slightly different notation, but it would mean the same thing. It always means a change in energy. Okay. So continuing on our discussion, at times we're going to have add even more subscripts to our symbols, right? So if I do v sub 1x, that would mean the x component of my velocity at time 1. Right here I need to specify both as the x component and the time. Okay, or I could do v sub 0 sub x, right? That would be the x component of my velocity at time 0. Or I could do v sub I sub x. That would be the x component of my velocity at the initial time, right? So you can see how we're going to have to use many subscripts to specify unique properties of a given variable. At other times, the subscript is going to specify an object. If you have multiple objects in a problem, you may have object A and object B and object C. We're going to use subscripts to denote those. So E sub 1 sub A would be the energy of object A at time 1. Right? And in rare cases, we need to keep track of 3 things at once. For example, you could have a problem that's a 2-dimensional problem, so you need to keep track of x and y, and you could have multiple objects, so you may need to keep track of A and B, and you may have multiple times, so you may have to keep track of time 1 and time 2. Right? So v sub 1 sub x sub A would be the x component of the velocity of object A at time 1. Okay? And then continuing on our discussion of notation, textbooks in general, as I said, are not very consistent with notation from book to book, or even within a book. They may change notation from chapter to chapter. So it's good just to get comfortable with this, because in your career you may see many different notations. Right? And when you're solving a problem, make sure you're very clear of what notation you're using. Maybe define it, maybe write it out in words. Right? Anything you can do to communicate to whoever is grading your homework or your test that you understand is a good thing you want to do. So do your best to communicate to your grader. But in this class, I'm going to try to keep a certain notation. I'm going to try to use numbers to represent different times. So E sub 1, again, would be in the energy at time 1. And I'm going to try to use capital letters to represent different objects. So E sub A would be the energy of object A. Okay, now that we've gotten all of that notation detail out of the way, let's talk about displacement. Okay, displacement is a word that means a change in position. Okay, so in one dimension, I may start off at x equals 3 at time 1, and at some later time, at time 2, I'm at x equals 5 meters. Right, so I've moved from one location to another. In 2 dimensions, I may move both in x and y, so I may move from x equals 2, y equals 4 at time 1 to x equals -3, y equals 9 at time 2. So I've moved both in x and y, and I'm going to use the subscripts, x sub 1, y sub 1 to represent time 1, and x sub 2, y sub 2 to represent time 2. Okay, so that's the concept of displacement. Now let's define the displacement vector. All right, this is physics. Everything we're doing is based on vectors because we need to denote not just how far we've traveled, but also the direction. Right? If I told you I moved 2 meters, that wouldn't tell you much. But if I told you I moved 2 meters in the positive x direction, that's a very useful statement to make. All right, so that's why we're defining the displacement vector. So again, the displacement vector magnitude is how far you've traveled. The direction of our displacement vector is the direction you traveled. Right, so here I've drawn in a displacement vector where it has a length of 2 meters and it has a direction in the positive x direction. So that is my displacement vector. And again, non-mathematically, you should be able to say I moved 2 meters in the plus x direction. In this example, I start off at time equals 1 at x1 equals 3 meters, and then I move to x equals -2 meters. All right, so I moved 5 meters as I walked from 3 to 2 to 1 to 0 to -1 to -2. That's a total of 5 meters of distance, but I also want to specify which direction I'm walking. Right, I walked 5 meters in the -x direction. Right, so that's what makes this blue arrow my displacement vector. It has that direction info. Okay, so how do we define this more mathematically? And again, we've got a few different symbols we're going to use. At times we may just use a capital D for displacement with the arrow above it to specify this as a vector, or we may just say delta R because this is our definition of displacement. It is the change in our position or the change in our position vector. So delta R is equivalent to displacement. So at times we could just use that notation. So what does delta R mean? This is R2 minus R1. So this is my position vector at time 2 minus my position vector at R1. Okay, I can always write out a position vector. A position vector is just my x component I hat plus my y component j hat plus my z component k hat. Right, my position in x, but I need to keep that in front of the I hat to keep those separate. Right, so what is R2 minus R1? I can always break that up into components because we know how to subtract vectors. So I'm going to subtract the x components of these two vectors and put them in front of the I hat. I'll subtract the y components, put those in front of the j hat, subtract the z components, keep those in front of the k hat. Right, so in the end, we end up with our displacement being defined as my change in x, I hat, plus my change in y, j hat, plus my change in z, k hat. Okay, and I already mentioned the notation here. So, okay, in one dimension, this simplifies a lot. Right, in one dimension, we don't have to worry about moving in y and z, for example. We're just moving in x. So my displacement in one dimension, as this chapter is based on, is just my final position in x minus my initial position in x, and it's, for example, in the I hat direction if we're moving along x. And since we're only moving in one dimension, we may not have to be as careful as keeping around the j hat and the k hat, for example, because they're always going to be 0. We may at times just talk about displacement as a component of a vector instead of a vector. Right? So the component of this displacement vector in one dimension is delta x. So if I want to calculate my displacement in one dimension, I can just calculate delta x, or my final position, minus my initial position. Right? So if I'm moving in a more positive direction, my final position is going to be larger than my initial position, and this is going to be positive displacement. If I'm moving in the negative x direction, x2 is going to be smaller than x1, and I'm going to have negative displacement. Okay, let's do some more examples. Let's go back to our original example, really, and plug it into our formula. Now that we have a formula for displacement, final position minus initial position, well, my final position, my position at time 2, is x equals 5 meters. So I plug that in here for x2. My initial position was x equals 3 meters, so I plug that in here. So my displacement is 2 meters. Okay, and so this is conceptually and mathematically telling us that we're moving in the plus x direction because this is positive. I'm moving along the x-axis because I have that I hat, and 2 meters is the distance I've traveled. Right, that's the magnitude of our displacement vector. Okay, let's go again. Just a quick note. In one dimension, we could have simply talked about our components again and not written this out as much in vector form. But I think it's important to realize what the vector form is. Okay, let's go back to this example. this time my final position is -2 meters, so I plug that in here for x2. My initial position is x equals 3 meters, so now I do -2 minus 3 meters, and my displacement is -5 meters I hat. So this time I'm moving 5 meters in the negative x direction. Okay, and just so you know, you could do this instead of using math, you could do it with our vector notation, because we know how to add and subtract vectors, and we're using position vectors to denote position, right? So if I move from here to here, right, my initial position vector is just a vector that starts with the origin and points to my initial position. My final position vector is again a vector that starts with the origin and points to my final position. So if I want to calculate my displacement, final position vector minus initial position vector, I can take my final position vector r2, I can subtract my initial position vector r1, and we know how to subtract vectors. This is the same thing as doing r2 plus negative r1, which is just flipping around r1. And now I can use the tail to head method to add these two vectors together, and that gives me my displacement, my delta r, right, which is the same thing we got over here just by drawing the picture. Okay, but this way of thinking about things in terms of vectors may be helpful to you in certain problems. And to get a little more practice, let's just look at a few more examples of displacement. So we want to calculate delta x, or final position minus initial position. And in these first three examples, we have exactly the same displacement. Each of these examples is 4 meters of displacement. So it doesn't matter where I'm starting, if it's positive or negative or what. What matters is that I'm just moving 4 meters in the plus x direction, and that gives me the same displacement. It's for this reason that we're going to use displacement to define things like velocity, right? Because it's not going to matter where you are. It's going to matter just how far you're going in a certain amount of time. Okay, and these three examples on the bottom, these are all examples of negative displacement. In fact, they all have -3 meters of displacement. Right here we go from 1 to -2, that's -3 meters of displacement. Here we go to 5 to 2, so we're still walking 3 meters in the minus x direction. Here we go from -1 to -4, still we're walking 3 meters in the minus x direction. Right, so those are all -3 meters of displacement. We may also do one-dimensional problems in the vertical direction or in the y direction. Right, so in this case, we would calculate delta y, or y2 minus y1. So in this case, I'm moving from y equals 1 to y equals 5. So to calculate my displacement, I do my final position, which is 5, minus my initial position, which is 1, and so my displacement is 4 meters. Okay, and let's go over to the right side here. In this case, I start at x equals 3, and I move to y equals 3, and I move to y equals -4. So my displacement is my final position, -4, minus my initial position, which was 3 meters, so -4 minus 3 is -7. So in this case, I'm moving 7 meters in the minus y direction. Okay, and one last thing on this section, I'm going to introduce the concept of a motion versus time graph. And this is actually an interactive example of this, so you can click on this link here, and it'll take you to a nice interactive, it'll open up in your browser a nice Java applet that will let you play around with this. And you can move this person around and graph position versus time. And it turns out that this graph, where on the y-axis I graph my current position at any given moment, and on the y-axis I graph my time, right, in this case in seconds, this is going to be a really important tool for our conceptual understanding and for solving problems. Right, so from this graph, I should be able to already just conceptually in words describe the motion. Right, so at time equals 0, right here, I can just read off my current position. I'm at x equals 5 meters, and I can tell that for the first second or so, right up until time equals 1 second, I stayed at x equals 5 meters, so I was at rest. I was just sitting right here at x equals 5 meters. I can see that then my position started getting smaller and smaller and smaller. So that tells me I started off at 5 meters and I was walking slowly in this direction, and I just passed my origin at this moment, and I continued walking in the minus x direction until I got to about x equals -4 or so. So I started off here, and I slowly walked until I got to x equals -4. I then just stayed at x equals -4 for almost 2 seconds, right? That's what's happening here. I'm just not moving, okay? And then at this moment in time, I started moving in the plus x direction. You can see that my position is getting closer and closer to 0. I'm passing 0 and then moving away from 0, right? So that's motion to the right in the plus x direction. I get back to x equals 5 meters. I stop for a second or two, and then I start moving backwards again. My position gets smaller and smaller and smaller, goes to 0, and then gets more and more negative. So here I'm moving to the left in the minus x direction during this time period here, and I can actually tell I'm moving very slowly during this period because the amount of distance I'm traveling, which is kind of the change in the y-axis here, right? It takes a long time for me to go from x equals 5 to x equals 0, for example. It takes 5 seconds or so. Okay, so I can kind of tell I'm moving slow. So hopefully this will be helpful for you in interpreting problems. And just as an example, if I gave you a graph like this, you could figure out the displacement. Right? If I wanted to know the displacement from x equals 6 seconds until x equals 10 seconds, we'll take a moment and try to figure that out. Pause the video if you want. Okay? But we can do that right now. At x equals 6 seconds, I am at x equals minus 4 meters or so. At x equals 10 seconds, I can read off that I'm at x equals 5 meters. So my displacement is my final position minus my initial position. So my final position is x equals 5 meters. That's where I am at x equals 10 seconds. My initial position was x equals minus 4 meters. So that's 5 minus minus 4, or 9 meters. All right, so as I walked from this position to this position, I walked 9 meters. Okay. If I ask you what was your displacement from x equals 10 seconds until x equals 14 seconds, for example. Oh, I'm sorry. Okay, we did that right. Okay. At x equals 10 seconds, I'm at 5 meters again. At x equals 14 seconds, I can read it off. That's about 2.5 meters. So my final position is 2.5. My initial position is 5. So 2.5 minus 5 is negative 2.5. Okay, so that's an example of negative displacement. And so hopefully these graphs will be helpful to you.